but I'll do my best, and I'm very happy and proud to make this first experiment with the Séminaire of Montreal. So let's do it. So the title, as you see, is Fuse the Hecke algebra and centralizer of representation of quantum groups. This is a joint work with my friend Nicolas Crampé, who is, I think, watching me right now. And so the goal of the talk basically is, so I'm going to introduce and motivate this new class of algebra called Fuse the Hecke algebra, and to explain to you why we are so interested in them. So I will start with the first part as an introduction or motivation. I will recall many well-known facts about the classical, the usual Hecke algebra. So the usual Hecke algebra, it's a very nice algebra. It has several equivalent definitions depending on which topic you are interested in. So let me start with one of the most natural, maybe, or the easiest one. It has something to do with the braid group. So this is a braid, a mathematical braid. So you see a braid on 5 strands, which are allowed to braid each other, to cross each other like this. And well, okay, so this form a group because, as you can see easily, you can take 2 braids, and so you can put another braid below the first one, concatenate, remove this, delete this line, and this will give you another braid. So they form a group under multiplication like this, and it's a very interesting group first, sure, and it's quite a complicated group. It's an infinite group, and its algebraic structure is very intricate. But for us, we can understand it very easily in an algebraic way by giving generators and relations. So it's quite easy to see that the braid group, any braid, is generated by elementary braiding. So sigma 1 here, for example, the first strand going over the second one, it's the first elementary braiding sigma 1. Then you have sigma 2, sigma 3, sigma 4. If the strand on the left goes under the strand on the right, it's the inverse actually of sigma 4, so sigma 4 inverse. And so as a whole, sigma 1, sigma 2, sigma 3, and sigma 4, they generate the whole braid group on 5 strands. Okay, and the defining relations are very easy. There are these 2 relations written here. So to see that they are actually satisfied by the elementary braiding is rather easy, but the statement, which is due to Artin, it's a theorem, is that they are enough. They are really these relations define exactly the braid group. Okay, so we have a group and it's very complicated. So one naive idea is to consider quotient of this group to make it simpler. And the first very natural quotient is the following. So for now, just forget this term and just look at this relation. This is equal to this. What does it say? It says that we can actually forget about crossings. So it says that you can replace a crossing by its opposite. In other words, you can forget all about the crossings here, and it's very easy to see that what you get then is just a permutation. If you have no information on the crossings, if you forget all about the topology, you only have the permutation, and so it's a symmetric group. So actually, it's a little bit too simple. We have lost too much information, and the Hecke algebra enters the picture like this. It's a very naive idea first. So let's take almost the same relation, but with a small deformation. So now the relation is like this. You can replace the crossing of this form by its opposite at the cost of this small correcting term depending on the parameter q. Algebraically, maybe more concretely, it means that we add this relation to the presentation of the braid group. So the relation saying that the square of a generator is actually expressed in terms of 1 and sigma I. Okay, So this gives you an algebra. This is the definition of the Hecke algebra. As you can see easily, if Q is 1, then this is just the symmetric group. So it's a deformation of the symmetric group. And this naive construction turned out to be extremely fruitful because it's basically responsible for the existence of the Jones, or more generally the Humfly-Petit polynomial, which is, I think, probably the most famous polynomial invariance of knots and links. Okay, so that's the first definition of the Hecke algebra. Second topic, the Yang-Baxter equation. So of course, I don't have time to explain to you the whole story of the Yang-Baxter equation. Let me just say that this is a very fundamental equation in mathematical physics. It basically allows you to build integrable systems in mathematical physics. So let's just look at its form. So what is the Yang-Baxter equation very quickly? Well, it's a functional equation. So it's an equation for a function, and this function takes a parameter, a complex parameter, which is called usually the spectral parameter, and takes its values in the space of endomorphism of V times V. So V is any vector space, V times V is a tensor product, and this is the space of linear endomorphism of this vector space. Okay, so this is a function, and the equation is a functional equation for this function. It's cubic, and it acts on 3 copies of the space V. And the notation that you have to understand here is that R1 means R acting on the 2 first copies here, V times V, first and second copy, and R2 is R acting on the second and third copies in this tensor product. Okay, so this is the equation. We are going to assume in this talk that we are interested in this equation, and we want to build, to construct explicitly solutions of this equation. Maybe a very easy remark is that it's very difficult to find solution because it's a functional equation. It's cubic in quite a large number of parameters. So it's an equation which is very difficult to solve explicitly. So we have to come up with methods to build solutions of this equation. And there is one method related to the Hecke algebra. So it's usually called Baxterisation. So take this formula. Remember, sigma I is the generator of the Hecke algebra, as in here, and define this function of alpha by this very simple formula, sigma I plus this term. Then you can check by very easy and explicit calculation that the Yang-Baxter equation is satisfied. What does it mean? It means that you're using the defining relation of the Hecke algebra to check that this expression satisfies this equation. So very nice, because we do have a solution of the Yang-Baxter equation, but we have to be a bit more precise. Actually, it's a solution which lives inside the Hecke algebra. This expression is in an algebra, in the Hecke algebra. So for physicists, it's not really useful. What they want is to have solutions on a space of endomorphism like this. So we have to add into the picture some representation statements, some representation theory. And it turns out that it's possible. So what is possible? Well, for any vector space V, there is actually, this is a very nice feature of the Hecke algebra, there is actually a representation of the Hecke algebra acting on a tensor space like this. So now we are in the following situation. We have this like formal solution of the Yang-Baxter equation in the Hecke algebra, and through the representation, we can send it to a solution in the endomorphism of a vector space. So we do get, at the end, solutions of Yang-Baxter equations on V times V. And what's quite nice also regarding this Baxterisation process is that this simple formula controls actually several solutions of the Yang-Baxter equation, because we can take any vector space V and build a solution on V times V coming from this simple formula. Okay, so the point here is that, well, first there is a simple formula like this, and then we have to appeal to representation theory to actually build solution. And this, the existence of this representation of the Hecke algebra is actually coming from a very deep theorem in representation theory. This is the Schur-Weyl.
Loïc, est-ce que je peux t'interrompre? John aimerait poser une question.
Oui, sure.
John?
Il a déjà répondu.
Ah, OK. Loïc, tu continues?
This is the best way to answer a question, right?
Yeah, it was easy.
Okay, so about the Schur-Weyl duality, the statement is like this. So remember, we have an action on the Hecke algebra on such a space. Say that the dimension of V is called D. Then what we have is that we also have the quantum group UQ of SLD acting on this space. If you don't know about quantum groups, you can maybe just forget about the Q and think of the Lie algebra SLD. So V is the vector representation of SLD, and we can make a tensor product, because this is what quantum groups are about. They are objects such that you can make tensor product of representations. And so we have this very nice situation where two different algebras are acting on the same space. And the theorem is the statement that they are both centralize each other. So this is the Schur-Weyl duality adapted by Jimbo for the quantum group setting, which asserts that the image of the Hecke algebra in the space of endomorphism of this space is exactly the centralizer of the action of the quantum group. And vice versa, the image of the quantum group is exactly the centralizer of the action of the Hecke algebra. So it's really a duality statement. Okay, so that's it. Yes, there is a question, I think.
Yeah, John again.
Yes, it's me again. This is just for clarity. So in the usual Schur-Weyl duality, let's say it is a Lie group or it's GLN or something on the one hand, and it's a finite group like symmetric group on the other hand. But the Hecke algebra is an algebra. So is the analog of the Schur-Weyl duality in this case, would that be the Hecke algebra's analog would be the group algebra of the symmetric group?
Yes, exactly. But the precise statement so if I forget Q, so the classical Schur-Weyl duality is that the centralizer of, say, GLV acting on this, it's not the image of the symmetric group, it's the image of the group algebra of the symmetric group. If you only take the group element of the symmetric group, you don't get the whole centralizer. So the centralizer of an algebra is always an algebra, and the classical Schur-Weyl duality asserts that it is the group algebra of the symmetric group. Exactly.
Could I just follow up with a mini question that was left over from earlier on? When you said that the Hecke algebra is a simplification of the braid group, did you mean a simplification of the braid group algebra?
Exactly. Sorry about that. So thank you. I can make this more precise. Of course, when we add this relation, we leave the realm of group, right? There is a minus here. So this defines an algebra. And it's a quotient of the braid group algebra. Sure. Sorry about that. So it's a simplification of the braid group algebra. From the point of view of representations, I always forget that the group and the group algebra is not exactly the same thing. So yes, thank you.
Okay, thanks.
Algebra is a quotient of the braid group algebra. Okay, so I move on. What I want to say is just, yes, for example, If the dimension is 2, so in the simplest case, then it's UQ of SL2 here. V of dimension 2 is what's called the spin 1/2 representation. And you have to understand that the statement of the Schur-Weyl duality is not exactly that the Hecke algebra is the centralizer of the quantum group. It's the image of the Hecke algebra which is the centralizer. It doesn't have to be a faithful action. In other words, there is a kernel. So the image of the Hecke algebra is a quotient, again, of the Hecke algebra. And in the situation where D is 2 for SL2, this quotient is very well known and it's called the Temperley-Lieb algebra. Right, so let me conclude this introduction by summarizing it. So we have this algebra, the Hecke algebra, and it has three very nice features. First, it has something to do with braids, and it's very fruitful for knots and links invariants. Second, there is an explicit, I should say, very simple Baxterisation formula leading to matrix solutions of Yang-Baxter equation. And from the point of view of representation theory, it allows to understand the centralizer of the quantum group action on a tensor space, which is very nice from the point of view of representation theory. So now the goal of our work with Nicolas is quite easy to explain. You see, I'm going to replace the Hecke algebra by another algebra, asking to have the same properties. The goal is now to define a new algebra depending on an integer k, such that, well, they will have something, hopefully they will have something to do with braids. We would like also to have a Baxterisation formula leading then to matrix solution of Yang-Baxter equations. So Baxterisation formula plus some representation theory. And it would be ideal if they also had something to do with centralizer of quantum groups. And this will turn out to be the case, of course. And the representation I'm going to consider are the following ones. So you see, remember V is simply the vector representation of UQ SLT. What we can do is to take the symmetric powers of this representation. So the kth symmetric power. Of course, if we are talking about quantum group, then we have to make some Q deformation. So it's a quantum kth symmetric power. It's really not important to know the definition of this. Just you have to know that this form representations of, again, representation of quantum group UQ. For example, if D is 2, then W, like this, is the spin k/2 representation of UQ SL2. And in fact, for SL2, this representation exhausts the set of irreducible finite dimensional representation of UQ SL2. We basically treat all the representation of SL2. For SLT, we have a special class of representations of the quantum group UQ SLD. Okay, so the algebra are going to depend on K, where K is the power here. And of course, when K is 1, this is simply V, and we should recover the usual Hecke algebra. So that is our goal. Right, so let me make a very short interlude about the fusion procedure. So you see in the title, and we are going to call this object the fused Hecke algebra. So I feel obliged to speak a little bit about the fusion procedure. So let me explain very quickly the idea of fusion, and these are the main ideas behind all the later constructions. So the idea of fusion is like this. It has something to do with the Yang-Baxter equation. It's really something which was created in the study of the Yang-Baxter equation. So let's say we start with a solution of the Yang-Baxter equation on V times V. For example, the solution coming from the Hecke algebra. Then the fusion procedure is in 2 steps. First step, there is a way to produce from this a solution on a much bigger space. v to the k times v to the k. And this step is quite easy actually. So I call it generic fusion, meaning that we have lots of free parameters inside the formula here. So it's very general and very easy to perform. For me, the important point is the following. We don't really want a solution on this huge space. What we want is to get a solution on this more interesting spaces. And it turns out that inside this big space, there is a subspace like this, plus some many other different representations appearing here that we don't really want. So what we would like is to have this solution not on this big space, but on this smaller space. So of course, the second step is to make a projection, to project this solution on this subspace. But this is, in my point of view, this is where the fusion procedure is very nice. This is where the miracle happens. Because of course, if I take any endomorphism of this space, there is no reason that I could restrict it to this one. So it turns out that it's possible for this solution, but for a very definite choice of the free parameters that we had. So there is a special point in the space of parameters which allows to make this projection and obtain what I will call the fused solution on space. Right, so this is the sketch of the fusion procedure. So you see two steps. First, larger space, and then a projection. There is a remark, a very important fact, but trivial remark. The projector, like the linear endomorphism projecting this space onto this subspace, well, it's almost by definition, it belongs to the centralizer of the quantum group. So from the Schur-Weyl duality, we can see this projector as living inside the Hecke algebra. So this is important.
Il y aura une question de John.
Okay.
John, vas-y.
Just slipping a quick question. You said there's a special parameter value
Yes.
where it restricts. Is this the same by any chance as the free fermion point?
No. I'm not sure. So I'm no specialist of that, but I'm not sure it's related. So maybe what I can say is that here you have n different parameters which are free, and they correspond to make the projection. You have to take them as the contents of some standard Yang tableau corresponding to this representation. So that's the most precise thing I can say.
Okay.
Okay, so this was the sketch of the fusion procedure. So you will see how it's related to our question. So basically, our original question with Nicolas was like this. Can we understand this solution as coming from a Baxterisation formula? If yes, in which algebras and what is the formula? So the way to answer is like this. The idea to answer is like this. So the basic solution was controlled by the Hecke algebra. The first step was just taking a much larger space. So we take a larger Hecke algebra, HKN, that's okay. And then the next step was projection, but projection on a vector space, that's okay. Projection on an algebra, what does it mean? Well, actually, as I said, the important fact is that this projector actually belongs to the Hecke algebra. So what we can do is answer this question, what is the fused Hecke algebra, like this. The fused Hecke algebra should be, from these ideas, should be a projected algebra like this. You take HKN, you see the projector as inside the Hecke algebra, and you multiply it both on the left and on the right by this projector. So this was the original idea. It could be a definition actually, but of course, understanding such an algebra is not easy task. It could be that this algebra is not very well behaving. So the goal is to actually give a nice description of this algebra. Okay, so yeah, before moving to the main part of the talk, let me just make a small remark. In this talk, for simplicity, I will only consider the situation where we have the same space, a tensor product of the same representations, SK times SK and so on. What in general we can do, and what we did with Nicolas, was to consider the most general situation like this, SK1 times SK2 and so on. So a mixed situation. And for example, if the dimension of V is 2, and if we choose to take K1 arbitrary, so K, but all the other Ks to be 1, so just the simple space V, then the fused Hecke algebra was actually studied under the name of Sim algebra. So again, this is for dimension of V is 2, so it has something to do with the Temperley-Lieb algebra. And well, you can recover it as a quotient of some particular choice of fused Hecke algebra. So yeah, this remark was just to say that there are many actually different algebras, I think, which are related to in some ways to the fused Hecke algebra. Okay, so the main part of the talk, the beginning, the first half was really motivation and introduction, but I will start from the very easy definition from now. So you can almost forget what I just said. I will introduce now an algebra and explain to you how it answers some of the questions I asked so far. So let's start back to basics now. Let's start with the symmetric group. So remember that the symmetric group Sn is the set of permutations of n elements, and you can see them as diagrams, nice little diagrams like this. So this is the identity element. This is the transposition of 1 and 2, transposition of 2 and 3, and so on. Permutation diagrams. And multiplication is obvious. It's by concatenation and just following the line. So you take 2 permutation, you put 1 below the other, and you just follow the line to perform the composition of that permutation. Very elementary. So what we want to define is an algebra like this. So now take the following objects. So diagrams, a little bit like this one, but with the following requirements. So we want 2 lines starting from each dot and arriving at each dot. So in general, K lines starting from and arriving at each dot. And so we take all different possibilities. So you have here 3 examples of such diagrams. These are very nice combinatorial objects. There is a finite number of them. You can try to count them. It's not so easy to find the explicit formula, but well, it's purely a combinatorial notion. If K is 1, obviously it's just permutations. But the problem is how to multiply these objects. Because you see, let's try. We take 2 of them and we concatenate, and then we should remove these intermediary dots, but there is some freedom, so some ambiguity. Should we connect, how can we connect these 2 lines with these 2 lines? Should we connect the first one with the first one and the second one with the second one, or the other way around? So the correct answer turns out to be that we should do all the possibilities and make the sum like this. So you see, removing these dots, we can remove it like this or like this. Same story for this one, like this or like this. So in all, we have, in total, we have 4 different possibilities. So we take just the sum of these 4 possibilities and we divide by 4 because it's a natural thing to do to normalize this product. So this is just simplifying a bit what we get. We have that this times this is going to be this expression. So this way, it defines the multiplication. So it defines an algebra structure on the set of objects, these diagrams, with the multiplication given by this definition. And this algebra, we want to call this algebra the algebra of fused permutation. It's HKN of 1, meaning that the fused Hecke algebra is going to be a deformation of this. So this is the situation when Q is 1, and the general situation is going to be a deformation of that. So how to deform? Well, of course, we should add, we should go back to some braid-like pictures. So we define the same sort of diagrams, but with braids now, with strands. So now the lines are not simply lines, they are strands in a three-dimensional space which can cross each other like this. So you have two different examples of fused braid. So same rule, two strands start from each dot and arrive at each dot, and they can cross and braid as they want. Right. So this is now a huge space. So we have to define, we have to impose some relations. So first, of course, as for usual braids, everything is considered up to isotopy of the strands. And we have some local relations. The first one is not very surprising. We impose the Hecke relation for each crossing. So again, you can replace a crossing by its opposite one, modulo correcting term. And the second kind of local relation is the idempotent relations, which says something about the crossings which are near this black dot.
Hello?
Yes, question, yes.
Yeah, I have a question. So isn't this a little bit the same as taking a special subgroup of the permutation of k times n objects?
No, not exactly. It's not a subgroup. Actually, it's not even a group. So it's not a subgroup of S k times n. It's obtained. Okay, it's really obtained like this. If you take SKN, so the group algebra, there is a certain idempotent projector which you can put on the right and on the left. And this expression defines an algebra, so not a group anymore, but really a subalgebra of the group algebra of SKN, K times N. And this is what I'm speaking about.
Okay, so I missed that. Thanks.
Excuse me, is it a subquotient?
Well, not directly. I mean, so not directly. In the semi-simple situation, after you understand the representation theory, you can see this maybe as a quotient, but not obviously. It's really it's a subalgebra.
A subquotient.
Subalgebra. Yes. So
a quotient of a subalgebra.
Okay. Yeah. So. In this sense, yes, because it's a subalgebra, but we have to be careful. It's a subalgebra where the identity element is different.
Okay.
So yeah, it's a subquotient in the sense that it is a subalgebra. Okay, so where was I? So it's idempotent relation. So we have also this local relation, meaning that a crossing near an ellipse can be removed. There is a power of Q appearing here and here, but basically you can remove crossings when they are close to the ellipses, to the black dots here. And note that the Hecke relation near these black dots, the sum, I mean the difference of these two relations is the Hecke relation. So it's like if close to a dot here, the Hecke relation is divided in two stronger relations. Okay, so to summarize, this defines the vector space. This vector space is the space of all fused braids modulo all these local relations. So how can we multiply them? Well, I'm going to be a bit quick here because it's almost the same as before. You put two fused braid on top of the other and you remove the internal dots with the same rule. every possibilities are allowed, but there are powers of Q appearing here and there. And you divide, instead of dividing by 4, you divide by these Q numbers. Okay. So there is a way to define the multiplication, deforming the multiplication that we had before for fused permutations. So at the end, what we have, at the end, we have the following things, objects. We have a family of algebras. So this defines algebras, well-defined algebras. So we have a family of algebras depending on n. N is the number of dots here. Here it's 2. And they form a chain of algebra. So they are obviously included into one into the other one, like this. They form a chain of algebras. They are finite dimensional algebra, but more than that, they are actually flat deformations of the combinatorial algebra of fused permutation. So in the combinatorial setting, the basis was naturally the set of such diagrams. And what this statement is saying is that this algebra, the fused Hecke algebra, is a flat deformation of the first one. So there is a basis also indexed by this combinatorial object. This is a very nice situation where we have a combinatorial algebra defined only in combinatorial terms, and the general case is the flat deformation of it depending on the parameter Q. Okay, these are what we call fused Hecke algebra, and we are going to be very interested in them. Okay, so the 3 different topics that I talked about. First one is the braid group. So where is the braid group inside this algebra? Well, it's there actually. Consider these braiding elements. So this particular fused braid where you take all the strands going out of I and you send them to I+1 going above the other ones from here. Well, you can check using the multiplication that I explained that it's an easy situation. You can check that this actually satisfies the braid relations. So they generate a quotient of the braid group algebra inside of fused Hecke algebra, which is what we wanted. And moreover, we know that they satisfy a characteristic equation of order k+1 and some other relations. For example, for k is 2, here is the characteristic equation, the cubic characteristic equation with the explicit eigenvalues. So we know in general the eigenvalues of the elements sigma I. So what we end up with are finite dimensional quotients of the braid group algebra inside the fused Hecke algebra. This is very interesting because it's, as you may know, it's quite difficult to find nice finite dimensional quotients of the braid group algebra. So here we have a family of them naturally appearing inside the fused Hecke algebra. Okay, so this was about the braid group. Second topic was the Baxterisation formula. So here it is on this slide. This was our main first result, and we are very happy with this. So yes, so this is a Baxterisation formula. At first sight, it may not look very beautiful, but it actually is quite beautiful if you look at it a bit more. So first, let me introduce some notations. Remember, we have these braiding elements. We also have partial braiding like this, when only one strand is going over the other one. And this is also a partial braiding where there is no braiding at all. This is the identity element. So our Baxterisation formula actually gives a formula as a linear combination of these partial braiding elements. And the coefficients are like this. So the more you look at them and the more beautiful they appear, you can see that first it's a very uniform formula. For every k, it's the same formula, more or less. If k is 1, you recover the simple formula that I showed on the first slide of the Hecke algebra. And the coefficients are very well organized, very nice expressions. They are completely made out of classical Q numbers. So this is a binomial coefficients. made up of Q numbers. This is the power of Q. And this actually is, these are Pochhammer symbols, quantum Pochhammer symbols. So in fact, very nice formula, and these coefficients appear very nicely because we chose this partial braiding as generators. Right, and you can see also that the dependence on the spectral parameter is explicitly written here. So it's obvious how it's immediate to tell what are the singular values of this function and so on. And it's also immediate to take the classical limit Q to 1, because these are all these are classical Q numbers, so you can just put Q to 1 in a very elementary way. Right, so we were very happy with this formula, but again, this is very satisfying for mathematicians, but for physicists, we should send this into representations, because for now it's a solution of the Yang-Baxter equation inside this fused Hecke algebra. So we have to be interested in representation theory. And this is the last topic I would like to talk about. So the complete statement of the Schur-Weyl duality is also available for fused Hecke algebra. More precisely, take a vector space V. Remember, this W was the symmetric, the case symmetric power of V. And what we have, well, we built the algebra for this property, so it's not really surprising, but it's very nice. We have an action of the fused Hecke algebra, a local representation on this tensor space. So already from this statement, what we obtain is solutions of the Yang-Baxter equation acting on this space W. So we recover this way the solutions coming from this representation of the quantum group QQSLD. So again, it's a shadow of a much deeper statement on the representation, which is a Schur-Weyl duality, and so it goes this way. Say now that the dimension of V is D as before, then again we have the quantum group QQ of SLD acting on this tensor space because it acts on W, and then you can make tensor product. And so we have the theorem which we expect, I guess, at this point. The Schur-Weyl duality is generalized to this setting. The image of the fused Hecke algebra actually coincides with the centralizer of the action of the quantum group. Okay. Oh, and also I should insist on the fact that this is for every dimension D, but the algebra here does not depend on D. In a sense, it's a sort of universal centralizer. It controls the centralizer of UQSLD for every D. But again, of course, this is only the homomorphic image of the algebra. So a next step will be to have an understanding of the kernel, to be able to describe more precisely the centralizer. For example, to be able to get the analog of the Temperley-Lieb algebra for k bigger than 1, so sort of fused Temperley-Lieb algebras. So I would like to explain what we know about this kernel in the remaining, like say, 15 minutes or so of this talk. And first, a slide to try to explain quickly how to think about this kernel. So you see what's happening when we do tensor product of representation. Something like this is happening. If we take, so first take V and V times V, then we can, it's elementary linear algebra, we can decompose it as a direct sum of the symmetric tensors and anti-symmetric ones. Symmetric square and alternating square. And then if we do V times V times V, it's a bit of the same story. We have the symmetric part, the anti-symmetric part, and we also have a summand of mixed symmetry, which is represented by a Yang diagram like this. So, and there is a multiplicity too. Okay, so this is really decomposition of a tensor space into irreducible components, very well known. And it goes on like this. and you see multiplicity appearing and more different representations. So how to think about the kernel? We can think about the kernel like this. This is perfectly true and very precise if dimension of V is large enough. So actually, if dimension of V is large enough, there is no kernel. The centralizer is all these representations appear, and the image of the Hecke algebra is isomorphic to the Hecke algebra. But when the dimension is small, then things start to happen. For example, if the dimension of V is 2, then if you think of a moment, it's impossible to make an antisymmetric tensor with 3 indices when the indices can take 2 different values. It's impossible. This space disappears. It's equal to 0. It's not here. And similarly, these 2 spaces are killed by the fact that the dimension of V is 2. Another example, if we take dimension of V is 3, then only this space disappears. So you see, the kernel it's exactly like this. We have a generic situation where the whole picture is here. And when the dimension is too small, part of the picture disappears. So some of the representations are killed by the kernel, actually. So when the dimension is small, some representation disappears. That's the main message here. So in an algebraic point of view, how can we kill the red representations directly inside the algebra? That's the main question. So talk about this slide. It's a bit heavy, but it's just to tell you that we have general theorem, and I will show you example in a moment. So there are 2 steps actually that we have to perform. First step is to understand the whole representation theory of the fused Hecke algebra. So don't read this, I will explain in the example, it will be simpler, I guess. And the second step is to say, okay, now that I know what are the representations, I should say which ones are killed by the kernel that I consider. This first step does not depend on D, and the second step depends heavily on the dimension D. Okay, so let me go back here. This picture is the first step, the whole representation theory, and these 2 examples are examples of the second step, in identifying which representations are killed by the kernel. Okay, so let's do this, and I will actually speak about the non-situation because it's going to be very similar. So how does it work for the Hecke algebra, for the usual Hecke algebra? Well, this is the Bratelli diagram of the usual Hecke algebra. So the whole representation theory is described here. At each level, for each n, the representations are indexed by, the reducible representations are indexed by partitions of n. And you can recognize maybe the multiplicity which were appearing in the decomposition of the tensor space in 2 slides before. Okay, so this is the first step, the whole representation theory of the Hecke algebra. Then, second step is what's happening if the dimension of V is small. So take 2, for example. Well, it's also well known that in this case, the representations which have to disappear are exactly these ones here. And if the dimension is 3, it's the same, more or less the same, but so all partitions with strictly more than 3 lines. Okay, and so the statement is so you can see that in fact, so there is a lots of representations which disappear, but they are all generated by a single representation, this one. Once we know that we have to kill this one, then automatically all its descendants are going to disappear as well. So in algebraic terms, the kernel is generated by a single element corresponding to this representation. For dimension 3, it's the same story with this representation. And so the answer is well known. In this case, the generator of the kernel is called the Q antisymmetrizer on certain number of strands, D plus 1. So for example, for UQSL2, this is the anti-symmetrizer on 3 strands, you see the sum of all the elements of the Hecke algebra on 3 strands with some carefully chosen coefficients. Right, and so the Temperley-Lieb algebra is exactly the quotient of the Hecke algebra by this element. What I mean by this element means that asking this element to be 0 gives you the Temperley-Lieb algebra. Okay, so now I can, if we all agree on this, now I can explain our results in the general, new results in the general situation. So first of all, description of the representation theory of the fused Hecke algebra for general K. So of course, I will only show you the example for K is 2. It's enough. So now you see the representation, the reducible representations are like this. At each level, you have partitions of 2 times n. So partitions of 2, partitions of 4. And they are obtained, so from one level to the other, they are obtained by adding 2 boxes. Obviously, so from this, you add 2 boxes, you get this, this, or this. And again, from this, you add 2 boxes, you get this one, and this one. But there is an important rule here. It's actually equivalent to the Littlewood-Richardson rule. You see, from this partition, I don't have the one with 2 lines, 1 box, 1 box. Why not? Well, because it's forbidden. So because it's forbidden to add 2 boxes in the same column. So that's the whole description of representation. You start with this partition. At each step, you add 2 boxes with the restriction that it's forbidden to add 2 boxes in the same column. For example, from here, you cannot go here because the 2 boxes are in the same column. Right, so this gives you the whole representation theory, and I'm a bit quick on it, but just to give you the idea, the next step, the last step, is to understand the quotient, the kernel. And the theorem is like this. If the dimension is 2, so it's very similar than before, if the dimension is 2, you have to kill all the representations with strictly more than 2 lines. So these 3 representations disappear because they have more, they have 3 lines, which is strictly more than 2. Okay, and this is a general statement. So for SLD, you kill all representations with strictly more than D lines. Right, but so it's in a sense, it's very similar than the usual Hecke algebra situation, but there is a big difference. Remember here, the kernel was generated by a single representation, this one. So it was quite easy actually to transform this into the Q anti-symmetrizer. It's almost elementary. But here it's much more difficult because the quotient, even in this example, the simplest one, K is 2 and the dimension is 2, the quotient is, the kernel is generated by 3 different representations. So it's going to be clearly much more difficult to identify a generator of this kernel. And so this is my last slide, and I will end with this. We have actually found that very surprising, very nice thing turns out to be true. So it's a conjecture in general, but I will explain to you when it's proved or not. So we are able to give a generator of the kernel as a single element, very easy to describe. Start with the Q anti-symmetrizer as before. So here is an example. So start with this element that we had in the Hecke algebra setting, but of course it's not an element of the fused Hecke algebra. So how to make it an element of the fused Hecke algebra? Well, the simplest way is the following: add vertical strands everywhere. You see from this to this, we just added vertical strands here, here, and here, everywhere, so that at the end, this element is a well-defined element of the fused Hecke algebra. There is stuff happening with the power of Q, which I don't want to explain, but it's explicitly given. And the statement is that this element is actually a generator of the kernel Yes, so a generator of these three different representations. So again, I say it's a conjecture because actually it's not. It seems very natural, but it's not obvious, and it's definitely not obvious to prove. So we were able to check this in many cases. For example, if you are interested only in SL2, then it's okay. For SL2, we were able to prove it in general. We are also able to prove it for any SLD if K is 2. So we have two quite nice situations where we proved it and we conjecture that it must be true. It must be true in general. So again, we have a way to understand the kernel. So, for example, if you would like to define an analog of the Temperley-Lieb algebra for the spin 1 representation of SL2, what is the answer at the end of this talk? Well, you start with the fused Hecke algebra, and you make the quotient by this element. You ask this element to be 0. It gives you a quotient of the fused Hecke algebra, and it's honest analog of the Temperley-Lieb algebra for the spin 1 representation. Right, so let me conclude and summarize what I've been talking about. So we defined a new class of algebras, the fused Hecke algebra, with a combinatorial plus braid-like description, explicitly. It does contain a realization of the braid group, so there is something to study here, which we are very interested, but we don't really know what's happening. We have a quotient of the braid group algebra inside the algebra, and it's very interesting. What we do have is an explicit Baxterisation formula, quite rather simple formula, and we are able to send it into representations to explicitly recover a solution of the Yang-Baxter equation, for example, corresponding to higher spin representations of UQ of SL2, but not only. And then the last part, the biggest part maybe, was that we have the full Schur-Weyl duality statement. So first, that the fused Hecke algebra surjects to the centralizer of UQ SLD, usually sometimes called the first fundamental theorem in invariant theory. And the second fundamental theorem will be to understand the kernel, and we have a description, conjectural in general, but proved in many cases, of the kernel. So at the end, we have this chain of universal algebra, the fused Hecke algebra, which such that for every D, they give you the centralizer as a quotient. And the kernel, depending on D, are explicitly described. So I guess that will be all. Yes, thank you for your attention.
Merci beaucoup, Loïc. Donc, ça a très bien été. Déjà, John a la main levée. Donc, je vais lui permettre. Ah, un instant, alors j'ai perdu John. Un instant.
Je suis là.
OK, vas-y avec ta question, John.
OK. En français ou en anglais? OK. I'll say it in English. So these fused Hecke algebra Baxterized, they give new solutions to the Yang-Baxter equations. Which lattice systems or spin systems these solve?
Well, so yes, so maybe I must say it again. Sorry if it wasn't very clear. In principle, we have this Baxterisation formula. So if we find the local representation of the fused Hecke algebra, we have solutions of the Yang-Baxter equation, possibly new solutions. But the way we construct them, we don't really have a new solution. We get the solution corresponding to the representation W of UQ SLD. For example, for SL2, we recover the higher spin solution of the Yang-Baxter equation. So in a sense, they were known, they are known, but it's not so easy to explicitly construct the matrix. And so our approach gives an alternative way or an alternative understanding of these solutions. And so to answer maybe your question, then, well, of course, these solutions, they just, they are associated to quantum spin chains, for example, with higher spin, not only spin 1/2, but any possible value of the spins. That's basically all I know about the integrable models behind all this.
Yeah, another question by Alexis. Just a second.
Oui, est-ce qu'on m'entend bien?
Oui, très bien.
Oui.
Donc, merci Loïc pour ta présentation. J'ai une question par rapport à ce qui s'est passé dans les slides au départ. Là. Je parlais qu'il y avait un lien avec les boundary seam algebras.
Oui.
Temperley pour c'est k égale 2, puis ensuite 1 pour les autres indices. C'est quelque chose comme ça quelque chose comme ça que j'ai vu, là.
Oui.
Donc, juste par rapport à ça, je ne sais pas si... parce que l'algèbre à couture, elle peut être définie donc, de deux manières, soit une version sandwich idempotent de Temperley-Lieb, ou soit un quotient d'une autre version de Temperley-Lieb. Je veux juste savoir le dernier théorème qui a été énoncé, est-ce que c'est exactement ça qui dit, soit qu'en général, la version sandwich idempotent a une correspondance quotient par un idéal? Donc, je ne sais pas si ma question est claire.
Oui, je pense que non, je pense que c'est un peu plus compliqué que ça, parce que je pense que l'algèbre des coutures, elle est définie comme sandwich par idempotent de Temperley-Lieb.
Mm-hmm.
Et c'est vraiment la même définition que nous, sauf que nous, à la place de prendre Temperley-Lieb, on prend directement l'algèbre de Hecke.
Oui, exactement.
Alors ensuite, c'est clair que comme Temperley-Lieb est un quotient de l'algèbre de Hecke, de la même façon, le sandwich de Temperley-Lieb va être un quotient du sandwich de Hecke, si je peux m'exprimer comme ça.
Oui.
Ça, c'est sûr.
Mm-hmm.
Et le dernier théorème explique comment... je suis désolé, je vais revenir hyper vite à la fin du cours. Voilà, ce dernier théorème-là explique comment passer du sandwich de Hecke au sandwich de Temperley-Lieb.
Oui, OK, c'est bon. Mais c'est que l'algèbre à couture...
Je pense pas que ce soit la même chose que ce quotient dont tu faisais référence.
OK, parce que les algèbres à couture se présentent aussi comme des quotients des algèbres blob, par exemple.
Oui, c'est ça. Et je pense que les algèbres blob sont... Donc, il se pourrait, ta question est peut-être, est-ce que les algèbres blob sont la même chose que fused Hecke algebra? Et je pense pas.
OK, c'est bon.
Je pense que soit blob, c'est un quotient intermédiaire entre les deux, soit elles sont légèrement différentes, mais elles ont toutes les deux un quotient qui ramène vers l'algèbre de couture. Je pense que c'est ça la vraie réponse.
Ça serait plus une coïncidence que l'autre chose, c'est ça?
Une coïncidence ou plutôt un fait qu'il y a beaucoup de façons de décrire les centralisateurs et l'algèbre blob en est une et fused Hecke algebra en est une autre, je pense.
OK, c'est bon, merci.
Merci pour ta question.
Une autre question de Luc. Vas-y, Luc. OK, un instant. Alors, les deux, on essaie. Ne touche pas à ton bouton. Vas-y.
Je suis habitué à gérer. Well, in English, so this was great work. Very nice talk. Thank you, Eric.
Thank you.
You did not talk about knot invariance. Anything to say about that?
Yeah. So you were able to see this, right? So the answer is that we don't know. We haven't studied so this is exactly this. We know that there is a realization of the break group. We know nothing about what is the quotient of the break group which appears in the fused Hecke algebra. We don't even understand all the relations which are satisfied by the braiding elements. And it's a very interesting question. About the knot and its invariance, I can say something more like intuitively what we could think is that this algebra, the fused Hecke algebra, play, okay, so this is a difficult sentence, play for this representation the same role as the Hecke algebra for the usual representation, okay? And we know that from the Hecke algebra, we can recover the quantum invariant corresponding to the representation V, the Humfly-Petit polynomial.
Mm-hmm.
So it's not a wild guess to say that in this algebra, there is a way to recover the quantum invariant corresponding to UQSLD and this representation, W. Okay, so maybe you know this, there is a way to produce a link invariant if you start from a quantum group and a representation.
Yes.
So I'm pretty sure that the answer is that this algebra controls in a way the polynomial, the quantum invariants coming from UQSLD and this representation W. This definitely has to be investigated because I think it's very interesting.
Mm-hmm. Thank you.
There doesn't seem to be any more questions, so I think we should give a hand to Loïc. I don't know how it works, but merci beaucoup, Loïc. And
le host, il m'a unmute pour que je puisse applaudir.
tous les donc merci beaucoup. Thank you to all who joined us. Next week we have Hendrik de B from Ghent, and so it was a pleasure to have you. See you next week.
Bye bye. Bye bye.
Au revoir.
Bye.
Bye bye.
So long, everybody.